Hey friends, if you're just ready for life to get back to normal, I understand, but remember that God's timetable is better than ours. Who knows what He's doing right now? When people have time to think about important things, perhaps they really are. This lesson is going to be about curve fitting, a second part. So the file name is section 3.5, 3.4, curve fitting part 2. There is also a Excel file, section 3.4, links return that goes with this. This material is not really covered in the text as such, but I want to illustrate another idea that is sometimes useful in modeling. It's most closely related to sections 3.4 and 3.5 though. So first of all, let's distinguish between linear and nonlinear curve fitting. Linear curve fitting we usually call linear regression. And so we've done that. And the question here is, can multiple linear regression be used to find the best values of the parameters in the model? So in all of these, x is the independent variable and y hat is the dependent variable, and then letters b, a, c, and so on are parameters that we're trying to estimate. Well, here's a quadratic model, and in the previous lesson, we indeed used multiple linear regression with independent variables, at least given to Excel, of x and x squared. And in case 2, I could use the independent variables for Excel, x and sine x. So yeah, we could do regression there as well. In case 3, not directly, but remember we have options. And so if we take the natural log of both sides, ln of y is ln of a plus bx. And the important thing is that here is a parameter and here is a parameter, and they're occurring in linear positions. And so yes, with a change of variables, we could do multiple regression there as well. But in number 4, something is different. Here's a parameter a, c, and b, and the b is inside of a sign. So I can't get directly in there to access it. And Excel cannot use multiple linear regression. You might briefly think, well, could I use an inverse sign or something to get the b out? Yes, but then the a goes inside of an inverse sign and you haven't helped yourself. So here's a situation where, nice try, but linear regression is simply not going to work to be able to construct a model like this. So let's show another way. First, I want to remind you of how we might evaluate models, or how we do evaluate models. Here are our definitions again for SS total, SS residual, and SS regression. And for multiple linear regression, we defined R squared as SS regression divided by SS total, the amount of variation explained by the model over the total variation. So if I use my relationship that SS total equals SS residual plus SS regression and solve for SS regression, I can write it this way, which simplifies to this, which I can interpret as 1 minus the fraction of the variation that's not explained. Now, the reason I'm going through all of that is that it turns out that for nonlinear curve fitting, it's not always true that this relationship holds. And so for R squared, let's just go with this definition that R squared is 1 minus SS residual over SS total, 1 minus the unexplained variation. And so the rest of the lesson is dealing with one example, one complicated example. In the spreadsheet, there are going to be the reported number of lynx furs sold by trappers in Canada from years 1919 to 1957. So lynx are wildcats, um, like a bobcat or a wildcat. And trapping was certainly legal in this time, and the number of pelts or furs that were sold were bought by merchants who were using them to make clothing, and they carefully recorded the number of pelts that they purchased. So we do have this data set. Here it is. I call it population. This is pelt population or number of pelts. And here is years since 1900. This is a famous data set, actually. If we go ahead and graph it, it looks like this. On the horizontal axis are years since 1900, starting with 1915. And here is the population or number of pelts. And what we see is, first of all, overall, there is definitely a downward trend. Over time, fewer and fewer pelts were being sold. And there may be various reasons for that, but let's go on and talk about other features of the data. The other interesting part is there's a definite up, down, up, down, up, down cycle. So that might be explained by climate patterns, perhaps by economic patterns. Maybe there's more demand for pelts at certain times in certain decades than in others. Or it might be reflective of the lynx population itself. So again, the lynx might be overeating their resources, and then the population declines and increases and so on. So very hard to say why this is happening, but we're doing empirical modeling, and so we're just saying, here's some data, and I want to fit a model to this. If I try a linear model, so back to the spreadsheet, here's the original data, and now there are several tabs. If I go to the linear trend, what I have done is graphed a scatter plot and had Excel add a trend line. It looks like this, and the R squared is only about 0.22. So it's not a particularly good model because it's making no attempt to follow these obvious seasonal trends going on. The reason I want to do that, though, besides just trying it, is to get my linearized residuals. After we take the linear model predictions and subtract them from the actual population, I get the linearized residuals, or residuals with the linear trend removed. And you still see this up, down, but now the overall downward trend has been removed. And so now, from this point on, it becomes a new problem, basically, is how do I fit this seesaw decaying sinusoidal looking variation? So we're going to use a sine function because that's the kind of thing that I'm most familiar with that oscillates. So reminder that for a sinusoid, there's something called an amplitude, something called a period, and something called a phase shift. And they relate to parameters A, omega, and C that appear in the sine function. Specifically, the amplitude is the magnitude of A, the period is 2 pi over omega, and the phase shift is this number C. Okay, so now I'm going to do a graphical approach. I take a look at the plot of the residuals and attempt to estimate the period, phase shift, and amplitude. Maybe I'll go here where the picture is a little larger. First of all, the period is usually easiest. Period is from, for example, peak to peak, or trough to trough, or where it crosses the horizontal axis on its way up. Any of those could be used. if I look at peak to peak, for example, I see the first peak that looks like right at 25, and then the next peak happening just about at 35, the next peak happening maybe just a little short of 45, the next peak maybe just a little short of 55, and so on. So it looks like the period is approximately 10 years. And so here I have decided to use the period t equals 10. Regarding the phase shift, the easiest place to see that might be right here. So the sinusoid is coming up and then down here, and it's crossing the horizontal axis here at about 22 or 22.5, something like that. So I'm going to use the number 22.5 for my phase shift. And then amplitude, and this is the difficult one because the amplitude is not constant here. This is decreasing over time. So I'm just going to, for a first start, to say, well, what's the biggest that this function ever gets? And it looks about, the largest residual is about 16,000. So as a first guess, that's what I'm going to use for my amplitude. So now I take these guesses for the parameters of the residuals and apply these formulas and crank out that I want to use A equals 16,000, omega equals 2 pi over 10, and C equals 22.5. So now I'm going to the third tab, sinusoidal fit. Here are A equals 16,000, omega equals 2 pi over 10, C equals 22. Here are my residuals copied from the previous tab. And now here are my predictions where I have A times sine of and my omega times the quantity T minus C. Notice there's a mix of relative and absolute addresses here. I do that and copy down, and here are my predictions for the residuals, for the linear residuals. And I generate a scatter plot of the time on the horizontal axis, the linearized residuals as the blue dots, and my predictions from this sinusoidal as the red squares, and I've added a curve, solid curve in so we can see them better. So how's it doing? Well, here's a trough at about the right place, a peak at the right place, a trough at about the right place, peak, and so on. It looks like the period is pretty good here. And as far as phase shifts, not bad either. I'm going through the horizontal axis at about the right place here, down, up, and so on. So I'm pretty pleased with my period and phase shift estimates. And as far as the amplitude, I knew that that wasn't going to be the final result anyway, because I haven't accounted for the decreasing amplitude of these oscillations, but not bad for a first start. So back on the notes, I have gotten to this point where I have the sinusoidal oscillation modeled except for the decaying amplitude. The way we'll do that is to use a damped sinusoid. So what we're going to do is take our sinusoid estimate and multiply it by a decaying exponential. So this is very common in modeling where the sinusoid is oscillating between what I can call an envelope of the form A equals A times e to the negative kx. And then down below here is going to be negative AE to the negative kx. As x or t gets larger, the decaying exponential gets smaller, and that squeezes the amplitude of the oscillations down, which is exactly what I want to do in this problem. So Then it's a matter of letting A and K play games with each other and try to get those adjusted so that the amount and speed of decay is appropriate for my data. This is not so much theory as trial and error, but as a ballpark, note that the number e to the -1 is about 0.37. So if I have a decaying exponential of the form e to the -kt, in 1/k time units, it's going to drop from peak down to about 37% of peak height. And if I look at the graph here, so maybe here is what I'm calling peak, and where does it drop down to roughly a third of that height? Well, it takes a while. When I get out to here, 10 years later, I'm still at over half the peak height that I was here. So I'm just going to take a guess and say that maybe I want to go 20 years or so before I say that the peak amplitude should be cut down by a third of what it started. And so actually 40 years, I think I did here. We'll adjust it later. So let's take K to be 1/40th, at which case 1/k is 40, and it takes my 40 years to drop down. So I'm going to use A now, larger, because e to the -kt is already doing some damping by the time I get to 25 years. I don't want to start at 16,000 here and decay from there, so I've chosen A to be quite a bit larger. Specifically, how about we take A to be 32,000? Okay, so now to the damped sine fit page. I've let A be 32,000, and omega and C are the same numbers as before. They won't change. Here's a K value, and what I've actually done is generate sliders here so that I can adjust A as well as K. And so now by trial and error, it's like, what should I do for the amplitude? If it were down here at 20,000, that's way too small. Let's ramp it up here. Maybe that's about right. I'm overshooting. My model is overshooting here and then undershooting. And I can also adjust the speed of decay. So I can control how quickly these things are going to drop down. For example, this value is not enough. This red model is not damping quickly enough to follow the blue data. I would need it up here some more. So what I've decided to do was go with these values after I had tweaked, of A being 32,000 and K being 0.0375. And when we do that, see, I said a 32,000. When we do that, we get a picture like this. And I say, okay, that's not too bad. Let's see then how we're doing overall. So now I want to go back and look at the original data compared to my overall model. So first is the linear part. We already generated that way back on the second step, I guess. And then here is the damped sinusoid part that we've just done. If I add those back together, that's my final estimate for the actual number of pelts. So here it is, finally on the final model tab, which is really busy. So I've color-coded some things. In the tan here are the original data. The blue is the linearization part. The olive green here is my damped sinusoid part. And then I've generated a graph here of the original data in blue, along with my damped sinusoid with a linear trend in red. And I'm pretty happy with this. I am not completely happy with this, but notice that the original data almost certainly doesn't follow an ideal damped sinusoid anyway. So maybe that's about as good as could be done. If I want to see how good I'm doing, I go ahead and compute my usual quantities involving measurements of error and crank out the R squared. And it turns out that this model has an R squared of about 0.8. One more thing I might want to look at as I'm evaluating model quality are the residuals. Now, these are the final residuals. So these are taking the original data way back in column B and subtracting my final predictions in column I. Then I generated a scatter plot of the residuals, and here they are. So what am I looking for here? Well, ideally, for my final model, the residuals would be purely random. I don't see that. I see positive residuals for a while, and then negative residuals for a while, and then they're turning positive again. I could see that in this picture as well. First, my model is not big enough, so I have positive residuals. Then in some places like here, I'm overshooting. I have negative residuals and positive residuals again. So I understand why that's happening. And at this point, I'm probably just saying I'm going to live with that because, again, this model form is not ever going to perfectly follow this data. And I think that is pretty much what we have to say. So we'll stop there. Thanks.